All right, so the last operation that our system can perform is the integration operation. So the integration operation also only requires one signal, so we're only going to use channel 1 here for our integrator. And so similar to the differentiator, the integrator will use the cutoff region, but instead of a high-pass filter, we'll use the cutoff region of a low-pass filter. So over here, just like with the differentiator, I have six integrators that each operate on a frequency range. So this one operates from 1 to 10, 10 to 100, 100 to 1,000, 1K to 10K, 10K to 100K, and 100K to 1 mega. And just like last time, I don't have to worry about anything higher than 1 mega because I had that anti-alias filter out any signal higher than a 1 megahertz in frequency. Just like with the differentiator, there's a bunch of inputs which can lead to fan out. So in order to prevent that, I have 2 buffers here. And these 2 buffers each handle only 3 integrators each to help reduce the strain. So with this, I can just load in the channel 1 signal just from before. So here's the channel 1 signal. All right, it's triangle, rectified triangle wave. So then it's going to integrate across each of the, it'll integrate using all 6 of these in parallel, just like with the differentiator. And then we'll need to choose the correct one afterwards. So first I'm going to run this. So I run this not for 10 micro, but for 1 millisecond. So this runs. This is still going to be plus minus 12 volts as per usual. And then, like I said earlier, this is almost the same as the differentiator, except now it's using low pass filters. And each of these operates under a similar range. So here we have different integrations. So let's take a look at each of these. Separate these curves. So the main one of interest we're going to look at is obviously this 10K or 1K to 10K. So the problem we see here is that it looks like it's slowly decreasing downwards and downwards. And that's because if you think about what a rectified signal looks like, see, I can take a quick preview of what the signal looks like. So this is what the channel 1 signal will look like. So the problem with this signal is that it has a DC value. So notice that it's above 0, so it has a DC average that's above 0, somewhere around here. Now, with the DC average of above 0, when you think of a constant and it's integrated, it becomes linear. And since these are all inverting integrators, it'll invert it downwards. So that's why there's going to be a negative slope on all of the lines, or on all the outputs. So as soon as I close this out here, that's why it looks like it's sloping downward. And most of these look like they're sloping downward because of that DC, because the integration of a DC is a linear relationship. So with that in mind, if we kept this running for infinity, eventually this would rail out to the minimum voltage of around 10 volts, 10 or 12 volts, which is the lowest voltage of the system. So from here, we just have to export this out as a text file. So I'm going to export this as integration. So now that we have that, I'll need to look at it in Excel again. So open it up in Excel. Integration looks like it's right there. All right, so it's tab delimited. All right, looks good. So the number of samples here, we see that again, it multiplies another about 4,000 samples. So I'll need to filter out every 10 sample and split it. So we're going to be using the filter macro. So I run this, and then I'll split these all out. As soon as it's done. All right, so now I need to save each of these as a text tab delimited file to be imported back into the to the next circuit to select which one of these to use. So there's that one. All right, that's 110. This next one, 10 to 100. 100 to 1,000. Oops. 1K to 10K. 10K to 100K. Then 100K to 1 mega. So, okay, good to go there. So just like with the differentiator, it performs all these in parallel, and it doesn't know which one to pick until later. So we go to integration select, and now we get to choose which one of these we're going to choose, which one of the outputs we're going to use we're going to use. So first we have to load all of our inputs. So this is integration 1 to 10. Okay. Integration 10 to 100. Integration 100 to 1K. Oh, that's differentiation. Integration 100 to 100K. There we go. Integration 1K to 10K. Nope, that's differentiation. Integration 1K to 10K. There we go. Looks like that. All right. Integration 10K to 100K. That. Integration 100K to 1 mega. All right, so now that we have all these selected, we have to select the right frequency range. So our frequency range is going to be 1K to 10K, which if this is 00, 01, or 000, 001, 010, 011. So the MSB is at the bottom, so this is going to be 011. So at the 011 right here, we'll select this line, which is 1K to 10K, which is the output that we do want. So if we run the transit here for 1 millisecond, let it run. And this is what we get as our output, which is what we want. So just like with the differentiation, there's a attenuation involvement operating in the cutoff region of the filter. And unfortunately, that attenuation might cause the scaling of this signal to be incorrect, but the general shape of this waveform is generally what it would look like. So notice how it looks like there's a DC value, which is what causes it to slant downward because it also inverts it. So this is the DC, the integration of the DC value is what this slanted line is. And then you have the actual triangle wave. So if the triangle wave is linear, the integration would be to the square, to the second power, so that's why it looks kind of wavy. And as it rides along that line downwards. So now we just need to export this as this is going to be our integration select. All right, I'm gonna open this up now here because just like with before, every time you operate, you end up with usually around 10 times as many samples. So I probably shouldn't have called it integration select because I believe that's what I called the final output, but as soon as I find it, integration select. All right, tab delimited, that's good. So just like before, scroll down here, 10 times as many samples. So that means we have to perform the filter operation to filter out every 10 samples. So close that out. So with this out of the way, we have only around 400 samples, just like normal. So then I'm going to save this. I'm going to save this as text delimited. This is going to be integration select. And I'm going to overwrite the previous integration select for this one with reduced number of samples. All right. So with that, we've covered all the operations that the oscilloscope system can perform. So to recap, the oscilloscope can perform simple pass-through just to see what the channel signals look like, inversion just to see what the signals look like if they were inverted, addition if you want to add channel 1, channel 2, subtraction if you want to subtract channel 1 from channel 2, integration if you want to integrate channel 1, and differentiation if you want to integrate channel 1 or differentiate channel 1. Those are all the operations that the oscilloscope system can perform. So after it performs all of those operations in parallel, it has to choose which operations it wants to output and be displayed digitally. So we'll cover that in the next video.